not belongs to A అయితే అప్పుడు what is the meaning? This is capital A is a limit point of x is A is a limit, small x is a limit point of A. So small x is a point ఏమవుతుంది అదని small x is a limit point of, so limit point of A. So limit point of every A is a limit point of A. X is a limit point of every point is a limit point. It's called as a derivative set. The set of all limit points is a derivative set. X does not belongs to A, but X is belongs to capital X. This is X is a limit point of A. The set of all limit points of a derivative set. That is the equal from A bar is equal to capital X. A bar is equal to capital X. Hence A is a countable dense set. Is a countable dense set. A countable dense set. A countable dense set. A countable dense set. So it's a clear. So this is a theorem is also countable a dense set. Next, Bolzano-Weierstrass property definition 4.3.12 in Bolzano-Weierstrass property. Now, what is a Bolzano-Weierstrass property? So, a metric space Bolzano-Weierstrass property. A metric space X comma D is a metric space. Is said to have a Bolzano-Weierstrass space. Is said to have Bolzano-Weierstrass property BWP. Bolzano-Weierstrass property if every infinite subset of X, every infinite subset of X has a limit point. Every infinite subset of X has a limit point. So X is a metric space. It has a one infinite set. It is a limit point in that limit point. So every infinite subset, Bolzano-Weierstrass property, a metric space X comma D is said to have Bolzano-Weierstrass property if every infinite subset of capital X has a limit point. Every infinite subset of a capital X is a limit. This is a definition, Bolzano-Weierstrass property. So next to 4.3.13 theorem. So this is 4.3.13 theorem. So we got now. Okay, now system. Now this is the Bolzano-Weierstrass property. So Bolzano-Weierstrass property. Okay. So this is the Bolzano-Weierstrass property. Next is 4.3.13 theorem. Sequentially compact. So 4.3.13 definition. The sequentially compact. What is the sequential? Let X be a metric space. Is said to be sequentially compact if every sequence in X has a convergent subsequence. And what happened? X comma D metric space. And actually what is X is metric space. Metric space and already we know that in class, metric space in condition. So X is a metric space is said to be sequentially compact is said to be sequentially compact if every sequence in X, if every sequence, suppose X in X, I think X has a convergent subsequence. Every sequence in X has a convergent subsequence. That is the limit point of the convergent subsequence in the limit point of a convergent subsequence is in X. So every sequence in X has a convergent subsequence, has a let X be a metric space, is said to be sequentially compact. X be a metric space is said to be sequentially compact if every sequence in X, ఒక sequence ఉంటుంది, a sequence, suppose xn is a sequence in capital X, it has a convergent subsequence. What is a convergent subsequence? Suppose xnk, xnk is a subsequence of xn, it is a convergent, it is convergent, that is called as a sequentially compact. So X be a metric space is said to be sequentially compact if it is every sequence in X has a convergent subsequence, that is a bracket. The limit point of the convergent subsequence, is in X also, both of them. So this is the two definitions we learn. What is the two definitions we learn is called is the definitions we learn now. So we have to learn two definitions is, so Bolzano-Weierstrass property, and also sequentially compact. So now we have to go to theorem 4.3.14 theorem. X is a sequentially compact metric space. X is a sequentially compact metric space. X is a sequentially compact metric space if and only if it is satisfies Bolzano-Weierstrass property. Sequentially compact, X is a sequentially compact metric space. Then we have to prove Bolzano-Weierstrass property. Next, conversely, we take Bolzano-Weierstrass property. We have to prove X is a sequential compact metric. In two conditions, sequentially compact. So we learn. So we have to two definitions are there. So Bolzano-Weierstrass property, it has X is a metric space. We have Bolzano-Weierstrass property. It has every infinite set infinite subset of capital X has a limit point. Sequentially compact is X is metric space sequentially compact if it is every sequence in X, it has convergent subsequence. These two. So these two definitions using the theorem is 4.3.14 theorem. So this is the 4.3.14 theorem. So what is the 4.3.14 theorem is called is? So proof. First one, let X comma D is a sequentially compact metric space. X comma D is a sequentially compact metric. Let us take an assumption. X comma D is sequential compact metric space. A be a infinite subset of X. Why sorry A infinite? We have to A, it has a limit point, then Bolzano-Weierstrass property. A has a so A be an infinite subset of X. We shall show that A has a limit point. And what is now? X is metric space. A is subset of X. A is infinite. So infinite. This is A has a limit point. A has limit point. I think that property name is called is Bolzano-Weierstrass property. We have to prove that. So what is the X is? So first one is X comma D sequentially compact metric space. So we shall show that A has limit point. So we got, since A is infinite set, since A is infinite, we can construct a sequence. We can construct, okay, infinite set, it has a construct a sequence. A is an infinite set. So we construct one sequence Xn. We constructed one sequence Xn of distinct points of A, distinct points of A. Okay. So the sequence Xn is the sequence in X. Since Xn a construction, the sequence Xn is must be in capital X. What is the capital X is? Sequentially compact set. What is the sense? So hand X is and also hand since X is a sequentially, a sequentially, a sequentially, a sequentially compact set, a sequentially compact, a sequentially compact quantity. This is. So what is the since X is a sequential compact? What is a sequential compact set to definition? We learn in previous. It has a convergent every a sequence in X. It has a convergent subsequence. Xn is the sequence in capital X. It has a one subsequence. There exists a convergent subsequence. There exists a convergent subsequence. And this is a sequence Xn is capital X. There exists a convergent subsequence Xnk is converges to small x. This is a symbol is convergent. The small x belongs to capital. It has a converges to small x. And what is the meaning? A converges to point x. We now show that and a converges to point. We now show that. So we now show that. We now show that. So we now show that. So what is now show that is x is a limit point of A. X is a limit point. X is a limit point of limit point of x is belongs to capital X. X is a limit point of A. X is a limit point of A. So what is now a subsequence? Xn k is a subsequence. Is converges to X. So what is the convergence definition? In BSc or also previous class. What is the convergence? There exists compulsory epsilon greater than 0 and small m, a small m belongs to capital and natural number. So it contains such that it's a open sphere. S x n k x n k comma x is less than epsilon. So for all k greater than or equal to m, for all k greater than or equal to m, then open sphere. So this is called as actually sometimes d good d of xn. And this is a sequence xnk is converges to x ante there exists epsilon greater than 0 and small m belongs to capital N natural number. D of xnk comma x is less than epsilon for all n greater than or equal to d with them d plus 1 in academic no problem. Some that is called as so this is the open sphere, then an open sphere, then open sphere. It is a open sphere. The open sphere is open sphere. The open sphere is S of x comma epsilon. S of x comma epsilon contains infinitely many terms. Contains infinitely many terms. Contains infinitely many terms. It has meaning. So this is called as infinitely many terms. So I think that is of infinitely many terms of the sequence xn. The sequence xn and therefore of A. Hence x is a limit point of A. X is a limit point of A. Infinitely many term of open sphere or neighborhood of anything. The open sphere is or neighborhood. S of open sphere is S of x comma epsilon is contains infinitely many terms. మీ టెక్స్ట్ బుక్ లో ఇట్లా కూడా ఉంటుంది S epsilon of x. S epsilon of x అన్న ఒకటే. This is called as open sphere. Is contains infinitely many terms of x. Many terms of the sequence xn. So therefore of A and therefore what is now infinitely many terms of x is a limit point of A. X is a limit point of A. X is the limit point of A. A that is called as the Bolzano-Weierstrass property. What is the capital A? A infinite subset of capital X. So this is the first part is completed. I am go to the conversely part. This is the conversely part. So what is the conversely? So we taken in conversely. So we take the conversely. Let the conversely part is, let us suppose that X has the Bolzano-Weierstrass property. Let X has the Bolzano-Weierstrass property. Suppose let Xn sequence be an arbitrary sequence. What is that? So capital X has a Bolzano-Weierstrass property. What is a Bolzano-Weierstrass property? Every metric space it has an infinite set. The infinite set it is contained. It has a limit point. Every infinite subset of X has a limit point is called as a Bolzano-Weierstrass property. So we take now Bolzano-Weierstrass property. So in arbitrarily, we take now xn. This sequence xn is arbitrarily sequence of x or in x, such that E is equal to, I am taking, what is the E is called? The orbital xn such that small n belongs to capital N. So E is equal to xn such that n belongs to n. We now the following two possibilities. E is a two possibilities. One time E is finite, one time E is infinite. So one time he is finite, what is the situation? Another case, he is a infinite, what is the second situation is also. Okay. Now it is called this. Now. Okay. So this is called this. What is this case is the first case. E is finite. So E is finite in case. E is finite. E is a finite case. When E is a finite, there exists is a small x is belongs to capital X. There exists a small x belongs to capital X, such that xn is equal to x. Finite. Now finite number of control is say infinitely many values of n. Infinite xn is equal to x. Infinitely. Hence here xn. So xn is equal to x. So same as the sequence is xn is equal to x. Xn number same continuous. The x is a constant. Has a constant sequence. Has a constant sequence. Constant sequence. And therefore every constant sequence is converted. Every constant sequence is converted. 100%. Every constant sequence is converted. Therefore, xn is convergent. Xn is convergent. Xn is also convergent. The sequence xn is, మనం ఏం చేయాలి? We have to do sequentially compact set. Sequentially compact set and we have to do. Now, a sequence xn in hex, it has a convergent subsequence that it is called is a sequentially compact. I'm to take an Bolzano-Weierstrass property we have to prove is sequentially compact set. Okay. Now, this is a case one is a clearly. What is the case one is a clearly? Yes. So this is a case one is clearly. We know that. So he is finite. He is finite. So finite. What is the situation? Every small x belongs to capital X such that xn is equal to x. And the sequence xn is equal to x such that the sequence xn has a constant sequence. A constant sequence. Every constant sequence is convergent. The sequence xn is also convergent. This is called as first case. So we have to go to the second case. What about the second case? When he is infinite, E is a finite, very simple constant. Where is E is infinite? E is an infinite. So this is E is an infinite. So infinite, what is the situation? Then he has a limit point. What is the Bolzano property? Bolzano-Weierstrass property. What tell me Bolzano-Weierstrass property? Every infinite subset of capital X has a limit point. Every infinite subset of a capital X metric, every infinite subset of a metric space X has a limit point. This name is called as a Bolzano-Weierstrass. What is now? He is infinite subset of capital X. Bolzano-Weierstrass property, he has a limit point. 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 So this is E has a limit point. So in limit point, what is the limit point that we got is the neighborhood of open sphere. I'm taken open sphere. So this is, so it is called as open sphere. Open sphere. Open sphere. So this is a open sphere is. I'm taking S of x comma 1. We are either textbook low S of 1 comma belongs to of S epsilon of S1 of x. So it contains infinitely many terms. It has a limit point contains every open sphere contains infinitely many terms. That is a definition is called as a many terms of E. It is called as a definition is limit point definition. So hence there exists open sphere, there exists is a small one, n1 belongs to capital N, such that d of, so d of xn comma x is less than 1, epsilon 1. As before, s of x comma 1 by 2 also contains infinitely many terms of e, also many terms of infinitely, అక్కడ b పడ్డది e రాసుకోండి. So s of x comma 1 by 2 is also infinitely many terms of e, many terms of e. Hence we have n2 belongs to n. Appudu what happened? So we can do n2 belongs to n. So what about such a d of x2 comma xn2 comma x is less than 1 by 2, is less than 1 by 2. And what is the first situation? What is the first situation? D of xn comma x is less than 1. So it is taken, there exists a natural number n1 belongs to n. It has a subsequence. Subsequence ఏమవుతుంది? D of xn1 comma x is less than 1, is less than 1. And s of నేను మళ్ళీ s లో ఏం చేస్తున్నా, it is x comma 1 by 2 అయితే this is n2 belongs to capital N. We have such that అప్పుడు ఏం కావాలి, this is d of xn2 comma x is less than 1 by 2. This is the first case. D of xn1 is comma x is less than 1. So this is, so we will continue for the way. Ante what happened is n2 greater than, third time x n3 belongs to n x n3 comma x is less than 1 by 3. So 1 by 3. What is of 1 by 3? So what happened is 1 by 3. For n2 greater than n1, after solve, proceeding likewise, we construct a sequence. Xnk, a construct sequence xnk such that it is continuing the process. The first time d of xn1 x is less than 1. Next time and dx of n2 is less than 1 by 2. Next time d of xn3 is less than x is less than 1 by 3 till continue the process. And d of xnk comma x is less than 1 by k is less than 1 for all k belongs to natural number n, for all k belongs to natural number 1. And this is called is first n2 belongs to d of xn1 x is less than 1. So d of subsequence xn2 less than 1 by 2. D of xn3, so this is x is less than 1 by 3. Will continue up to so on proceed. D of xnk comma x is less than 1 by k for all k is belongs to natural number. So for all k belongs to natural number. So for all k belongs to natural number. So this is a now xnk, the sequence xnk. ఇప్పుడు ఏం చెప్తుంది? The sequence xnk is a subsequence of xn. So that converges to small x. The xn1 is also converges. And what your meaning is called is it clearly now? Is చూడండి x d of this is d of xn1 e comma x is less than 1. అంటే మీనింగ్ ఏంటిది? xn1 అనే సబ్సిక్వెన్స్ నాగరాలు ఉంటే తీసుకోండి. సార్ గారు ఓకే. d of xn2 comma x is less than 1 by 2. xn2 is converges to x. xn2 is converges to x. xn2 is converges to x. So next time d of xn3 is converges to x is less than 1 by 3. Meaning ఏంటిది? This is xn3, a sequence is converges to x. almostly d of x and k of x is less than 1 by k. The sequence x and k is converges to x. What is the sequence xn? This is a sequence xn k is a subsequence of xn. Original sequence xn. xnk is a subsequence. And a sequence is xn is of x. It has a convergent subsequence. That is name is called is sequentially compact set. That name is called is sequentially compact set. So Koti, we have to take an x and k is a so Koti last step. This is called is hence xn has the sequence xn has a convergent subsequence. Xn has a convergent subsequence. Xn has a convergent subsequence. A convergent subsequence. Xn has a convergent subsequence. A convergent subsequence, and so that capital X is sequentially, sequentially. So this is sequentially compact. So what is a sequentially compact set? A sequence xn, because any metric space, it is a sequence. It has a convergent subsequence. That metric space is called is sequentially compact. So this is a clear now. So this is a 4.3.15. So 4.3.15 is no, no. It is called is no. Now it is called is now a compact metric space satisfies Bolzano-Weierstrass property. A compact metric space satisfies Bolzano-Weierstrass property. This is a 4.3.15. A compact metric space satisfies Bolzano-Weierstrass property. BWP Bolzano. So compact metric space satisfies Bolzano. Let X be a compact. X be a let X be a compact metric space, compact metric space, compact metric space, compact metric space. So and A be an infinite, and A be an infinite. So and infinite subset of and A be infinite subset of capital X, and A be infinite subset of capital X. A be an infinite subset of capital X. So AB an infinite subset of capital X. So compact metric space Bolzano callante it is a infinite subset. So A has no limit point of and this is so A has infinite subset. A has no limit points. Then for X belongs to A, there exists a open sphere S of X. Open sphere S of X such that and what is now A has no limit points. Then for X belongs to A, then for X belongs to A. Now this is so A has limit. So there exists an open sphere S of X such that X belongs to A implies S of X intersection of A is equal to a singleton X. A singleton X. So and X does not, X belongs to A. What about X belongs to A in the case? X belongs to A case, so what happens? Open sphere X of X intersection of A is equal to singleton X. Okay. X does not belongs to A, say X belongs to A. This is the meaning. Open sphere S of X intersection of A is equal to singleton X. So next case, X does not belongs to A, say what happened is this is the open sphere S of X intersection of A is equal to empty. This is a empty. So since X is equal to, since capital X is equal to, since capital X is equal to arbitrary union of in small x in belongs to capital X, S of X and arbitrary union and capital X is compact, X is compact, X is compact, X is compact. So there exist numbers, x1, x2 up to so on xn is belongs to capital X, such that so this is A is equal to, what is that? X is equal to arbitrary union of small x belongs to X in open sphere S of X. S of X. Capital X is compact. Compact contained it contains a finite subcover. So there exists x1, x2, xn belongs to capital X. It is a finite A subset of capital X is equal to union of I is equal to 1 to n S of xi, same. A subset of capital S of xi, and what is our meaning? This is x1 comma x2 comma up to on xn. This is a contradiction. A is containing a finite subcover. Can actually what happened? I'm starting is capital A set is infinite set. Capital A set is infinite set. We got a result is A is a subset of containing a finite subcover, which is a contradiction to our assumption. So this is the contradiction. 2, A is infinite, hence A is infinite. A is infinite. So A is infinite. Hence A is infinite set. So therefore, our A is infinite set, we are contrasting A has a limit point. Hence, so not a limit point, that's why A has a no limit point of this. A has a no limit point is wrong. And starting is A has no limit point and this for X belongs to A. This is a wrong 100%. So therefore A has a, hence A has a limit point. A has a limit point in X. A limit point in X. X has, capital X has Bolzano-Weierstrass property. X has a Bolzano. What is the X is? A compact metric space. Every compact metric space is Bolzano-Weierstrass property satisfies. So that is a property is completed. Next is, now this is called this 4.3.16. So is our definition is called this Lebesgue measure. What is the Lebesgue number? Lebesgue number. So the Lebesgue number is let x comma d a metric space. The x comma d is a metric space. X comma d is a metric space, be a metric space, and x comma d a metric space, and this is called this set of G alpha such that alpha belongs to high. Behind open cover of X, if there exists a number, A belongs to R, this is a small a number, is A greater than 0, A subset of X, D of A less than 0, diameter of A, D of A less than A, diameter starting. So therefore A subset of G of alpha. So this is, since alpha, then A is called is, then small a is called, is Lebesgue number of the open cover. Lebesgue number of the open cover. Lebesgue number of the open cover. So Lebesgue cover number of the open cover. So this is open cover. So we have to next definition is called this a big set. What is a big set is? This is a big set is called as a subset X is called as a big set. A subset X is called as a big set. So if it is not a contain, any member and a open set of the given open cover, if it is not contained in any number and a member is called of the given open cover, it is not a member of the open cover, that is called as a big set. A subset of X is called as a big set if it is not contained in any member of the open cover. Directly open cover, every open cover containing open set. So it is also note. So big set definition note 1. So if X has no big set, every point, every every positive real number is a Lebesgue number. X has no big sets. Every positive real number is a Lebesgue number. Second, if A is a big set, then A has at least 2 points of X. Then A has at least 2 points of X. So big set, okay, big set with a compulsory it has at least 2 points of X. D of A equal to infinite. This is a D of A is equal to infinite. So therefore, for every big set A, then every positive real number a Lebesgue number. Every is for every big set A, then every positive real number is a Lebesgue number. Is a Lebesgue number. So this is called as one way. Now other. So this is a theorem. So 4.3.17. So what is the 4.7.3.17 theorem is? In a sequentially compact metric space, every open cover has a Lebesgue number. In a sequentially compact metric space, every open cover has a Lebesgue number. So Lebesgue number. So that is called as. So this is in a sequentially compacted metric space, every open cover has a Lebesgue number. Proof. X comma D is a sequentially, this is. So let X comma D be a, so be a sequentially compact metric space. I'm taken C is equal to, this is a G alpha such that alpha belongs to high, be an open cover, open cover of X. So this is a behind of open cover. This is called X gamma D metric space, and C is equal to the set of all G alpha belongs to high. Is an open cover of X. If possible, wrong sentence. X has no Lebesgue number. X has no Lebesgue number. Then for no Lebesgue number, one of the point note. X has no Lebesgue number. So then no Lebesgue number. Then each small n belongs to n. There is a non-empty subset of B n of X such that. So this is of S of B n of is less than 1 by n. So our delta of B n of is less than 1 by n. So this is a delta of Bn is less than 1 by n. So Bn is not subset of G alpha for all alpha belongs to high. This is the equation 1. Choose a point. Xn is belongs to Bn. So Bn for each small n belongs to n. Capital X is a sequentially compact to the sequence. Xn is a must contain a subsequence, say Xni, the sequence Xni. So which is a converges to X. X is a sequentially compact set. And X is sequentially compact set. Xn is a sequence. It has a subsequence Xni is converges to X. X is a sequential compact entity, is a sequence Xn of X that has a convergent subsequence. So Xni is converges to X. So since is open cover, okay? This is a C is a set is a, since C is a open cover, G of alpha such that alpha belongs to is a open cover of is a hand open cover of X, open cover of X. So is a open cover of X. There exists and a point and a open set There exists a open set G alpha belongs to C such that X is belongs to G alpha. G alpha is a open. There exists G alpha is a open set. Open set definition is G alpha is a open. So the open set definition is there exists is epsilon greater than 0 such that so S of X comma epsilon or is subset of a containing every a set is containing is open. A set is containing this open set call it a set is containing this open sphere. That set is called is open set. G alpha is a open set a containing is open sphere or SS of X is subset of G alpha. A G alpha is set containing its open sphere. That G alpha is called as a open set. Is a open set. So that is called is. So S alpha is subset of G alpha. This is the equation number 2. So equation number 2 is a clearly. Now again, now this is. So we are go to this way. Now the last page also. So the last page also. For this, for the above epsilon greater than 0, for the above epsilon greater than 0, for the above epsilon greater than 0, xcni is a converges to x, and also delta of xcni so is tends to 0 has k tends to infinity, if there exists is k naught is a belongs to capital N, k naught is a belongs to capital N, such that we can do right here d of xni comma x is less than epsilon by 2. So delta of bni is less than epsilon by 2. So y be any arbitrary point. So y is a belongs to arbitrary point of b and I. So now using in 3 is a triangular inequality, and up to d of y comma x and I is also less than epsilon by 2. And one part is d of x and I comma x is less than epsilon by 2 and d of x comma x and I is less than 1 by 2 and the same. Next also d of y comma x and I is less than epsilon by 2. D of y comma x it's also. So d of y comma x in triangular property. What is the triangular property? D of y comma x and I plus d of x and I comma x. This is less than or equal. This first is a epsilon by 2. So epsilon by 2 is also plus epsilon by 2 is equal to epsilon by 2 is equal to 2 is cancelled. We got is epsilon. We got is epsilon. So what is now? So y is arbitrary points. So the y and a point comparison y is a arbitrary point of y belongs to s of x comma epsilon. So in subset are equal to g of alpha. And y is a belongs to the open sphere s epsilon of x in subset of g alpha. And what is b? Y is a belongs bni. Bni subset are equal to s epsilon of x subset of g alpha, which is a contradiction to equation 1. So which is a contradiction to equation 1. So our supposition that in this one, our supposition that uh, if possible, our supposition that x has no Lebesgue member is wrong. 100% x has a it has x as a it is x as a Lebesgue number. So which is a contradiction to equation 1. So it is hence so C is equal to the set open set G alpha such that alpha belongs to height is a has a as a Lebesgue Lebesgue member Lebesgue measure Lebesgue number also. This is Lebesgue number. So is Lebesgue number. So it is Lebesgue number. Now Lebesgue number. Now it is the part is a clearly and totally in today I am to discussion is called this. Totally we got is 5 pages. And totally 11 pages we discussion. The topic is called this discussion is all of you. Now again, now given epsilon greater than 0, if there exists. topic in page number 44, totally bounded sets. X be a metric space. X be a metric space. So X be a metric space, X be a metric space. So this is X be a metric space. So given epsilon greater than 0, there exists a finite subset of A. A is a finite subset of capital X. So X is equal to X is equal to union of in small a belongs to a union of small a belongs to capital A. Capital A. This is S epsilon of S epsilon of A. S epsilon of S epsilon of S epsilon of A. So this is S epsilon of A open sphere. I think that is called is A is called is epsilon net. Epsilon net. What is the definition? Is epsilon net? That is the epsilon net is equal to. So that is epsilon net is equal to. What is the epsilon net is? Capital X is equal to. So this is epsilon net is equal to capital X is equal to, is a union of small a belongs to capital A. This is S epsilon of small a. Ikkada what is? A is subset of capital X, finite subset of X. So then A is called, this is A is called epsilon net. Epsilon net. So epsilon net to a metric space. Epsilon net a metric space. X is said to be totally bounded. So what is the this is epsilon net. A metric space is said to be totally bounded if it has epsilon net for each epsilon greater than 0. Epsilon if it has epsilon net. So a metric space X comma D is a metric space is a totally bounded. Totally bounded if it has so if it has epsilon net. What is now? X comma D is a metric space. Is said to be totally bounded. Is said to be totally bounded. This is said to be totally bounded. So is said to be totally bounded if it has epsilon net. What is the epsilon net? So X comma D is a metric space. B subset of X. DB the restrictions of D to B. Then B is said to be totally bounded. B of DB is a totally bounded. A is epsilon net, then A is a finite and hence bounded. A is a epsilon net. And what is the meaning? A is epsilon net. Epsilon net and it is A must be is a finite and bounded. A is a finite and bounded. A is a finite and bounded. So A is a finite and bounded. A is an epsilon net, then A is a finite. X is a totally bounded. It is also bounded. So X is totally bounded, then it is also bounded. A is epsilon net. X comma Y belongs to S. There exists A comma B belongs to A. What is now? This is X comma Y is belongs to capital X. What is the capital X is? Totally bounded. So then there exists compulsory. Small a belongs to capital A. Such that compulsory. The small x is belongs to S epsilon of open sphere A. So next Y is belongs to S epsilon of B is a open sphere of B. So what is the distance? D of X comma Y, D of X comma Y is a less than or equal to what happened? D of X comma A plus D of A comma B plus D of B comma Y, D of B comma Y. What is this triangular equality? D of X comma Y less than or equal to D of X comma A plus D of A comma B plus D of B comma D comma Y. So B comma Y. So this is called is less than. This is a value is epsilon. This is a value is epsilon. Is epsilon. This is a 2 epsilon plus D of A antam. This is a diameter of A. So if Y is a metric space, X is subset of Y, then X is totally bounded. Then X bar is also totally bounded. So what happened? Y is a metric space. X is also metric space. 2 metric spaces. So X subset of Y untadi. Then so X is totally bounded. X is totally bounded. So Y is also Y bar. Y complement is also Y bar is also totally bounded. So Y bar is also totally bounded. So we turn in next topic is around bounded set example. Next, a sequentially compact metric space, a totally bounded in page number 45 theorem. So we got some examples also. So tomorrow, two theorems are there completed. Two theorems, that topic is completed. Tomorrow next is a new topic, is a connected set also discussion. Connected set and continuity and also. Okay. So what happened is, this is a today a discussion is epsilon neighbor, epsilon net. So totally bounded epsilon net to totally bounded, it has must be epsilon net. It is called as a total bundle. What is the epsilon net is called is? So this is capital X is equal to, so capital X is equal to a union of capital X is equal to epsilon net to it should be. So we got X is equal to union of. So we got X is equal to union of small a belongs to capital A. That is called as S epsilon of A small a. S epsilon of small a. So that is called is epsilon net. Okay. Now in tomorrow we'll discussion is called is a totally bounded topic, and also in 4 point connected sets also 4.7 connected. So tomorrow 4 point sets now.
Thank you, sir.
Okay, all of
Thank
you
you,
are
sir.
okay. I'm to my PDF notes are followed. So are you understand?
Yes, sir.
Okay. 13 members వచ్చారు now. సో ఇక్కడ మీరు అంబేద్కర్ ఓయూపీజీ సెంటర్ లో నా క్లాసులు విన్నారు కదమ్మా?
సార్
విన్నారు కదా? ఓకే కదా?
విన్నాం సార్.
ఆఫ్లైన్ సార్.
ఆఫ్లైన్ లో విన్నారు కదా? అర్థమవుతున్నాయి కదా?
అవును సార్.
విన్నాం సార్.
ఓకే రైట్.
సార్
చెప్పండి అమ్మా.
ఎగ్జామ్స్ ఎప్పుడు సార్? వెన్ విల్ బి అవర్
ఐడియా లేదమ్మా, ఇప్పుడైతే క్లాసెస్ కంప్లీట్. మేబీ నాకు జూలై ఆగస్ట్లో ఉంటాను మేబీ.
ఓకే సార్.
ఓకే
అయితే సార్ ఒక డౌట్.